Essa é uma aula pública, é uma aula de ciência, mas para o povo em geral. Então não esperem que nós vamos resolver equação, não vamos. Nós vamos resolver equação. Ah, ele ficou muito sentido lá. Calma. A gente vai resolver na prática. Mas essa é uma ocasião especial para a Universidade de São Paulo, porque nós estamos recebendo aqui na Universidade o encontro geral, a Assembleia Geral da IUPAP. Todo mundo aprende nos livros, que é quem coordena unidades, símbolos e tenta, de alguma maneira, verificar como anda a física de um modo geral. A IUPAP, que é International Union of Applied and Pure Physics, ela tem um objetivo, ela tem condições, e ela quer ter certeza que contribui com a sociedade e com o avanço do conhecimento. Então é uma ocasião muito importante para a gente, porque é a primeira vez que a IUPAP, com sua Assembleia Geral, vem para a América Latina. E nessa ocasião, nós achamos que seria apropriado também valorizar a ciência, fazendo uma aula pública. Tá certo? E nós temos hoje uma dupla sorte. Nós não temos apenas o professor Phillips, que é Prêmio Nobel de Física de 1997, mas temos também o professor David Wineland, que é o Prêmio Nobel de 2012 em Física. Ambos estão presentes, embora o showman vai ser o Bill Phillips, o David está dando todo o apoio, como ajudou a carregar as mesas. Ok? A aula vai ser em inglês. Nós não contratamos tradução por duas razões. Primeiro, que é muito caro, e depois a gente acha que inglês hoje é a linguagem científica e que mesmo uma aula dessa deve motivá-los a acompanhar. E eu sei que muitos de vocês falam inglês. E nós temos também na aliança membros da IUPAP, dispersados por aí, né, os que estavam participando dos encontros de ontem. Ok, now I'm going to start in English. It's a very big pleasure for us to have a IUPAP in Brazil this time. And IUPAP is a union that is made to serve society. We are trying to do the best in physics to help society. And nothing better to demonstrate this as giving a lecture of physics for the general public. So the president of IUPAP, Professor Bruce, is there. So let's give a huge thanks. And I want to thank you all for coming. We have 130 delegates from many countries in the world meeting in the University of São Paulo. They don't know that Thursday is a holiday in Brazil. We're going to keep working. And I also want to thank Bill and David for coming. David is one of the fantastic scientists in metrology and trapping ions, and he came to give a talk on the workshop. He's not actually participating in the General Assembly, but he is a very good friend of Brazil. And Bill Phillips too. I don't even know how many times they came to Brazil. I remember they're working in my laboratory in São Carlos much before they were thinking about Nobel Prize. And today they are very important guys, and they still keep coming to Brazil, helping us, discussing physics and everything. So I want to thank you a lot, and I hope you all keep coming to Brazil, because you are a Brazilian in the heart. So, okay, we're going to start the lecture. The title is Time, Einstein, and the Coolest Stuff in the Universe. This lecture concerns time, how we measure what it is, how we cool down, why cool down matter, why is that important for metrology, and many things also that Bill will tell. So Bill, please, let's start the lecture.
tremendous pleasure for me to be in Brazil again, in São Paulo again. So many wonderful things here to experience and so many new and exciting things to learn. Tonight, we're going to have some fun. We're going to talk about time, Einstein, and the coolest stuff in the universe. And the first thing I should do is to thank the people who give us the money to do this. NIST, of course, where I'm from, the Office of Naval Research, the National Science Foundation that supports our Physics Frontier Center, and in the spirit of shameless advertising, especially with so many young people here, when you're thinking about changing from one stage of your educational career to another, remember us at the JQI. There's lots of opportunities for undergraduate and graduate study and postdoctoral study, and we do a lot of really exciting things, only a little bit of which I'm going to tell you about tonight. And of course, there's this warning that interesting things may happen during this talk. Now, before I go further in this talk, I want to remember a very special lady. Kathryn Kenny was my laboratory director for over 20 years. She was the founding director, the only director of the physics laboratory at NIST. And during the time that she led that laboratory, she created an environment where over a space of 15 years, 4 Nobel Prizes came out of her laboratory. I think she was the only person in the world who ever had 4 Nobel laureates reporting to her at the same time for work they had done under her supervision and tutelage. She was an amazing person. She was a tremendous friend of IUPAP. She served on IUPAP for many years, and through IUPAP and in other ways, she advocated for women in science and for underrepresented minorities. And she really supported the people who worked for her. The thing that was so important to her was the success of her people. And this wall in back of her desk was covered with posters that celebrated the prizes that various people in her laboratory had gotten. Well, let's come back now to time, Einstein, and the coolest stuff in the universe. One of the things I want to emphasize is that I'm part of the NIST Laser Cooling and Trapping Group, and it's my tremendous pleasure and honor to work every day with Gretchen Campbell, Paulo, Trey Porto, and Ian Spielman, who are the permanent members of that group, and just such an amazing set of young people. Well, maybe they're not as young as they used to be, but they're a lot younger than I am. And it's so wonderful to be surrounded by such creative and active young people. Now, you might ask, okay, time, Einstein, and the coolest stuff in the universe. So what does time have to do with Einstein? Well, time put Einstein in the cover of the magazine as the person of the century. And I think it was a pretty good choice because Einstein did a whole bunch of things that really changed the way we think about our universe. Each one of these things would be worth a lecture in itself. But probably the thing that Einstein is most known for is his theory of special relativity. Before Einstein, people thought that space and time were like an unchanging stage on which the events of the world played themselves out, like the stage I'm standing on. And what Einstein taught us was that the stage was part of the action, that the things that were going on in the universe could change the very nature of that stage, that different people looking at the stage of space and time in different ways would see different things. The idea of the relativity of time, the idea that time is not the same for all observers, came not from this old guy, but from this young guy asking himself a question that people have probably asked themselves since the beginning of human time. What is time? What is this thing that is always in the present but will soon become the past? Why is tomorrow always a day away? People have thought about these kinds of questions for centuries and millennia, and the answer that Einstein gave may seem to you to be a little bit superficial. Einstein said, time is what a clock measures. But by taking that idea seriously, he came to the understanding of the relativity of time. But if time is what a clock measures, then you may ask yourself, what is a clock? Well, to me, a clock is anything that ticks, something that gives you a regular series of events. The earliest clock is the rotating Earth. Now, ancient people didn't know the Earth was rotating, but they saw the sun rise and set every day, and that allowed them to tick off the days. When they became more sophisticated, they made observatories like Stonehenge and were able to understand the timing of the seasons. They made sundials and were able to tick off hours. Much later, Galileo, according to legend, was sitting in the cathedral in Pisa. And apparently he wasn't spending very much time paying attention to the worship service. Instead, he was watching the chandelier in the cathedral swing back and forth. And the thing that he noticed, timing the swinging of the chandelier with his own pulse, he noticed that whether the chandelier was swinging a little bit or whether it was swinging a lot, it took essentially the same amount of time to go back and forth. This constancy of the period of a pendulum led people like Christian Huygens to develop a clock that would use that kind of a ticker as its timekeeper in clocks like this, this tall clock or grandfather's clock. Now, some of you may be wearing a clock on your wrist, as I am. Looking at the age of most of you, you're probably getting your time from your cell phone rather than from a wristwatch. But us old people used to tell time by having a clock strapped to our wrist. And inside this clock is a quartz crystal that is shaped like a tuning fork. And the vibration of that quartz crystal is the ticker for the clock in this wristwatch. Now, there are many different kinds of clocks. All of these clocks have different kinds of tickers, and all of these clocks' tickers are imperfect. So while Galileo was able to show that the period of a pendulum is nearly independent of how far it swings, it certainly is not independent of how long the pendulum is. So a pendulum may stretch or shrink, and that would change the ticking rate of a pendulum clock. Every quartz crystal is made a little bit differently, and it may change its ticking rate depending upon whether you wear it on your wrist or whether you put it on the table. And even the rotation of the Earth is not constant. The tides and changing ocean currents slow down or speed up the rotation of the Earth. The fact that this was so was made clear to me in a rather dramatic way one day when I was visiting the United States Naval Observatory. Now, navies have been interested in time since people started to sail on the open seas, away from land. And I was visiting a colleague there who was going to show me the latest thing in clocks. And as we were walking toward his laboratory, we passed by a door on which it was written, Director of Earth Rotation. It seems like a pretty responsible job. You wonder what happens if he goes on vacation. The point is, somebody keeps track of the changes in the rotation of the Earth because there are people who need to know this. Astronomers who need to know exactly where to point their telescopes, people who navigate using the stars need to know this information. So all of these clocks are imperfect in one way or another. The very best clocks are atomic clocks, where the atoms are the tickers. Now, why can atoms be the tickers for clocks? Well, as you probably learned in high school physics or chemistry, atoms have certain energy levels. And the difference between those energy levels corresponds to a frequency. And that frequency can be the ticking frequency for a clock. And the thing that is wonderful about these atoms is that for every atom of the same kind, that ticking frequency is exactly the same. By international agreement, we have decided that a certain number of ticks, about 9 billion ticks of a cesium atom, a particular isotope of cesium, cesium-133, the 9 billion or so ticks of that atom equals exactly 1 second, by definition. And the wonderful thing is, it doesn't matter where you got your cesium. You could get your cesium in Brazil, you could get it in France, you could get it in the United States. The ticking frequency will be exactly the same. As far as we know, you could get it on the moon or on Mars or in a distant galaxy, and the ticking frequency will be the same. And it's very little affected by the environment. So these atomic tickers make the best clocks. Now you might ask, how good are these clocks? Well, for less than 300 reals, probably a lot less than 300 reals, you could get a clock as good as my watch, which is good to about a part in a million, or 30 seconds in a year. But if you're willing to spend 300,000 reals, then you can get a clock that's good to a part in a million, or 30 seconds in a million years. Now you laugh, 300,000 reals for a clock. But think about this. You pay 1,000 times more money, but you get 1,000,000 times better performance. I think that's a real bargain. But you still might ask yourself, who really needs a clock that is that good? Because after all, in order to go about our daily lives, we don't really need to know what time it is to that level of accuracy. Or so you may think. I now want to convince you that you are very happy that someone is keeping track of time to that level of precision for things that you do in your daily life. I found this advertisement in a magazine once. It said, if you buy this car, this expensive car, and you get into trouble, relax because help is only 10,000 miles away. Well, of course, this is a civilized country, not like the United States. And so let's say 20,000 kilometers. But the point is that what they are advertising is that if you get into trouble, you can rely on the global positioning system, the satellite navigation system, to tell somebody where you are so that they can send somebody to help you out. Now, how does that global positioning system work? How are you able to tell where you are anywhere on the face of the Earth to within a few meters? And the answer is atomic clocks. Clocks that are in a system of these 24 satellites orbiting the Earth. And inside every one of those satellites is a collection of atomic clocks that are of the quality that I talked about that costs 300,000 reals. Now, they cost a lot more when you put them in a satellite, but that's not the point. Anything that goes into space costs a lot of money. But these are really good clocks, the best commercial clocks that are available. So how does this work? How does having clocks in satellites allow you to know where you are? Well, whoops, that's not what I want to do. Let's go back. Okay, so each one of these satellites has clocks that are keeping time, and all those clocks are synchronized. Now let's imagine for a moment that you, with your satellite navigation receiver, also have a clock. You don't, but just for the sake of argument, let's assume that you do have a clock, and it is also synchronized, so that all these clocks are keeping the same time, as you can see here. Now, these satellites are broadcasting what time it is. They are also broadcasting where they are. So let's animate this and see what happens when the clock is broadcasting what time it is. Then it takes a certain amount of time for that information about the time to get to you. Isn't it amazing how often you have to use the word time when talking about time? So that time is just equal to the distance divided by the speed of light. And so because you know where the satellite is, and because all the clocks are synchronized, and you know the difference between the time that you're seeing on the satellite and the time on your clock, you know how far away the satellite is. So that means you know you're somewhere along here. Well, that's great. But of course, there's another satellite, and that makes it even better, because when the signal from that satellite gets to you, and you read what time it is, then you know you're at the intersection of these two curves, and you know where you are anywhere on the face of the Earth within a few meters. And people use these things for all kinds of activities in their daily lives. Taxis use them to find their way to the right auditorium here at the University of São Paulo. People who are delivering packages to you. Commercial aircraft and ships use them. Hikers take them out in the wilderness so that they don't get lost. Golfers use them to determine how far away they are from the hole, so that if they're good enough, they can select which club they should use to hit the ball at that distance. Earth scientists can use it to detect continental drift. If you're willing to wait a long enough time, the accuracy of the GPS system is on the order of centimeters. And people can tell how fast the continents are drifting relative to each other at the level of centimeters per year. So that's how wonderful and how useful the global positioning system is. So now you might ask yourself, well, what do these atomic clocks look like? Well, I found another advertisement in a magazine. It said that recently scientists in Braunschweig, Germany set the atomic clock back 1 full second. This was an advertisement for an airline company, by the way. And it said, our flight schedules have been adjusted accordingly. Yeah, right. The airline company isn't in business anymore. But in fact, atomic clocks are set forward or back a second from time to time. These are called leap seconds, and they're to keep the Earth rotation time in sync with atomic time, because atomic time is near perfect, but the Earth is constantly changing. And when the Earth gets out of sync with atomic time by 9/10 of a second, then they add or subtract a second. We had one last New Year's Eve. I'm not sure if you remember this, but last December 31st was 1 second longer than the day before. I hope you used that extra second wisely. I never understood why they referred to scientists in Braunschweig, Germany, because it's actually done at the International Bureau of Weights and Measures in Paris, and besides, this was an American airline company talking about the German Standards Laboratory, which is in Braunschweig, Germany, but none of that is why I'm telling you this story. I'm telling you this story to assure you that the instrument in front of which these two dorks are standing looks nothing like an atomic clock. In fact, if you were to go a few years ago to our atomic clock laboratories in Boulder, Colorado, you would have seen an apparatus that looks a little bit like this. Inside this long tube is an atomic clock where cesium atoms are used to tick off time. Here is an oversimplified version of how the atomic clock works. Imagine this is a cesium atom, and imagine there are two energy levels. There are a lot more, but we only care about these two particular energy levels that are a certain distance apart. And if we select the cesium atoms so they're all in the lower energy level, and then shine in microwaves at just the right frequency, and this is just the right frequency, a little bit more than 9 gigacycles per second, 9 billion cycles per second, then if the frequency is just right, it will make the atom change its state to the excited state, and we'll be able to measure that it changed. And if it's not right, then it doesn't do anything. So what you do is you just tweak the frequency. You just change the frequency a little bit until it makes the atom change state, and then you know you've got the right frequency, and you can broadcast that as a clock. Now that's the oversimplified version. This is the slightly less oversimplified version. We think of every cesium atom as a little tiny clock. We put the cesium metal. Now remember, cesium is a metal. You remember from your chemistry classes, it's on the periodic chart toward the left, down toward the bottom. It burns in air, but we do this in a vacuum, so everything is safe. We put it in a little metal can, heat the can up, and some of the cesium vaporizes, and some of the vapor atoms come out and make a stream along here that we call an atomic beam. Now when the atoms pass through this region where we have the microwaves, essentially what we're doing is we're synchronizing the ticking of cesium atoms to the ticking of our microwaves. And now what we're going to do is see whether they stay in sync. So we allow the atoms to go to the other end of the apparatus, and we check at the other end of the apparatus, which is about a meter away, whether they're still in sync. And if they're not, then we feed back to change our microwave frequency until it is in sync, and then we know that our microwaves are keeping the right time. This is sort of like what you would do if you want to find out whether your watch, if you had a watch, was keeping the same time as the correct time. What you do is go to www.nist.gov, my institution, and there will be a button to click for the current time. There will be an animated clock that will tell you what time it is, and you set your watch to that time. Now the question is, what is your watch fast or slow? Well, it doesn't do any good to come back after a minute to see whether your watch is fast or slow. Come back after a month and find out how many seconds your watch is fast or slow by. In other words, you need a long time to be able to tell how good your timekeeper is. It's the same thing here, but these atoms are moving at faster than 100 meters per second, and the other end of the apparatus is only a meter away. So that means you've only got a few thousandths of a second to make that measurement. So you don't have a month, you have a few thousandths of a second. This doesn't sound very easy. In fact, a friend of mine said this is like trying to tell time with a clock that's going past you at the speed of sound and crashing into the wall. Not so easy, but people have been working on this for more than 50 years, and these clocks are now better than a part in 10 to the 14. That means a part in 100 million million. But they can't get any better, and we want to do better. They can't get any better because the atoms are moving so fast. And there's several reasons. One is that, just what I said before, we have such a short time to measure the atoms that you can't do it much better than about 100 hertz. Out of almost 10 billion hertz, that might sound like a small amount, but it's nowhere nearly good enough for what we want to do. Plus, when the clock is moving, there's the clock being the atom, there's a Doppler shift. Now, what is the Doppler shift? Well, it used to be that everybody knew what the Doppler shift was because when a train went through your town blowing its whistle, you would hear the whistle make a sound like, I didn't do that very well. Anyway, the point is that the pitch is high when it's moving towards you and low when it's moving away. You can see the same thing if you go to the sea and measure the frequency at which the waves hit the shore. If you then got into a boat and went into the waves, those waves would hit the front of your boat at a higher frequency than they would hit the boat when it's on shore. And if you turn around and go back into the shore, the waves will hit the back of the boat with a lower frequency. So this is the way the Doppler shift works for water waves. It works the same way for sound, and it works the same way for light. It's the way in which we know that the universe is expanding. We look at different, very distant stars, and we see that the color of the light coming from those stars has a lower frequency, which means it's shifted toward the red end of the spectrum. And we know that those distant galaxies are moving away from us, and that's how we know the universe is expanding. Well, this hurts us when we want to measure from a clock because it shifts the apparent frequency of our atoms by a lot, by as much as a part in a million. And we want to do 100 million times better than that. Fortunately, there are all kinds of tricks to get rid of this shift, but the tricks don't work perfectly. And the degree to which they don't work is a major limitation in how good these clocks can be. And finally, Einstein taught us in 1905 with the relativity of time that moving clocks run slow. And our atoms are moving clocks and they run slow. And there's no tricks to get rid of that. You have to measure the velocity of the atoms and make a correction for the way in which those clocks are running slow. And the inability to do that perfectly, to measure the velocity distribution perfectly, is one of the things that limits the performance of these clocks. So what are we going to do? We want to do better than 10 to the minus 14. We are the National Institute of Standards and Technology. It's our job to do better. But how are we going to do better if these atoms are moving so fast? And the answer is, we're going to cool the atoms down. Because the difference between hot and cold is the difference between fast and slow. The air in this room is full of atoms and molecules that are moving really, really fast, about the speed of sound. This air in this room is pretty warm. I think I'm going to put my jacket off to help me cool down. That won't help the air cool down. Now let's see if I still got my laser pointer here. Okay, well, I don't know where it is. Okay, it's in my other pocket. That's great. Okay, the point is that if we could cool the air in this room down, what it would mean would be that we would be making the atoms and molecules move more slowly. In fact, temperature is simply a measure of the kinetic energy, the energy of motion of the atoms and molecules that make up the stuff that we want to measure the temperature. So, we're going to make these things cool down. So, how are we going to do that? Well, in order to give you some idea about how we're going to do that, courtesy of the good people here in the physics department in São Paulo, I brought along some really cold stuff. Inside this container, which is frozen to the table, inside this container is liquid nitrogen. Nitrogen is the main constituent of the air. That means this is like liquid air. It is so cold compared to this room that everything in this room is burning hot compared to this liquid nitrogen. Imagine what would happen if you were to take cold water and pour it onto a red-hot stove. You would find that the water would boil as soon as you poured it onto the stove. And that's what's happening to the liquid nitrogen. Because the liquid nitrogen is so cold compared to the surroundings. Now, if you've got something that cold, then to me it seems perfectly reasonable that you could use it to cool down a gas. So I've got a bucket here of liquid nitrogen. Let me just refill it a little bit here. Just put a little bit more in. Okay, now it's spilling over, so it's nice and full. So what I'm going to do is I'm going to take a traditional container for hot air and put it into liquid nitrogen to cool down the gas so the atoms and molecules move more slowly, because if the atoms and molecules are moving more slowly, then this is so much fun. So if the atoms and molecules are moving more slowly, then that means that we'll be able to measure them better. Okay, so let's see what else we can do to show you how cold this stuff is. Here is a nice bouncy rubber ball. Okay, I'm going to put it into the liquid nitrogen to see what happens. Okay, and while that's cooling down, here is a thermos bottle. Physicists call this thing a dewar, but it's just an insulated container that can keep cold stuff cold and hot stuff hot. It's been sitting out at room temperature all day. That means compared to the liquid nitrogen, this thing is burning hot. Imagine what would happen if you took a metal bucket and heated it up in a fire until it was glowing red, and then poured cold water into the glowing red metal bucket. What would happen would be that it would boil over. Don't try this at home. So while that's boiling away, cooling down the inside of the thermos bottle, let's cool down some more gas so that we can have a lot of a lot of atoms and molecules that are going slowly so that we can use them to make better measurements. Okay, so let's see where we are with this. Okay, there we go. Great. Okay, great. Now let's come over here to the thermos bottle again. Okay, the thermos bottle has stopped boiling. That means that the temperature of the inside is down to the temperature of the liquid nitrogen. So I'm just going to top it up a little bit to make sure it's nice and full. Now, here is a nice fresh flower. Just bought earlier today. Nice fresh flower. Sitting out at room temperature, compared to liquid nitrogen, this flower is red hot. It's even red. And imagine what would happen if you took a metal rod and put it into a fire until it was glowing red. And then you took the metal rod out and plunged it into a bucket of cold water. What would happen? It would make the water boil and spill out of the bucket, and that's what's going on here. So while that is boiling away, cooling down the flour, let's go back to the, what? Let's go back to the bucket and see if we can cool down some more gas to make the atoms and molecules move more slowly so that it's easier to measure. Okay, now maybe I blew that one up a little bit too much, but I'll just force it in. Yeah. You just have to push harder, and it'll be fine. I'll just put a little bit more liquid nitrogen. It's been spilling out, so we want to get more in here. Okay, let's close that out, and now let's go over here to our flour, and I look in here and I see that the flour it has stopped making the liquid nitrogen boil. That means the flour has cooled down to the temperature of the liquid nitrogen. When I pull it out, it's frozen so hard that I can crush it like it was made out of glass. This stuff is incredibly cold. And if you've got something that cold, then why not use it to cool down your gas that to make sure that your atoms and molecules are moving slowly. So, what? So let's cool down some more gas. Okay. Here we go. There. Now, let's see, what else can we do? I'm sure that when you were young, looking to see how young some of you are, when you were young and were learning how to do things in the kitchen, I imagine that your parents told you that you should never ever put a closed container of liquid into the oven. Well, here we have a container, and here we have some liquid. So let's put a little bit of this liquid into the container. Okay, now we're going to close the container really, really tight. And this room, compared to the liquid nitrogen, is like an oven. So let's put this closed container of liquid in the oven and see what happens. And while we're waiting to see what happens, let's put it out. Because we want to get Because when they're cold, they're not moving very fast. And if they're not moving very fast, then we can make better measurements. So let's see what we can do with those. Okay, that's going in just fine. Okay, great. Now let's see, what else do we have? Okay, let's have a look and see what this happens to this rubber band. Here's a nice, stretchy rubber band, okay? Now what I'm going to do is I'm going to put it into this container of liquid nitrogen. Now, you can't see it, but it's making the liquid nitrogen boil because that's what everything does if you put it into liquid nitrogen, if it's in room temperature, because the room temperature is so much hotter than the liquid nitrogen that makes it boil. Now, it doesn't take too long before it stops boiling, and when I pull it out, it's so stiff. I can break it like it was a dry twig. And all I have to do is to warm it up in my hands. And it's a nice stretchy rubber band again. This stuff is really, really cold. And, you know, if it doesn't that cold, and why not use it to cool down your gas so the atoms and molecules will move more slowly, because if they're moving more slowly, it'll be easier to measure them, and maybe we can make a better one. So, put those in there. Now, let's go over here and have a look at the rubber ball. So remember how nice and bouncy the rubber ball was? Let's see what it's like now. It broke like it was made out of porcelain. This stuff is really, really cool. Now, how cold is it? Now, we're used to measuring temperatures, the temperature of the air, the temperature of our body. We're used to measuring it in degrees Celsius. So on a nice warm day, it might be 35. If it's really hot, it might be 40. Right? Your body temperature is about 37. I don't know if it ever gets to 0 here, but where I come from, it goes below 0. Now, physicists don't like these below 0 temperatures. This is annoying to us. And so we've got a different temperature scale that we call the absolute temperature scale, or the Kelvin temperature scale, where the size of the degrees are the same as Celsius degrees, but the lowest possible temperature is 0, so there can't be any temperatures below 0. Now you might ask yourself, why is there a lowest possible temperature? Well, remember what temperature is about. It's about how fast the atoms and molecules are moving. What is the slowest you can move? The slowest you can move is stopped. So when the motion of the atoms and molecules stop, that's as cold as you can get, and we call that absolute 0. Now, it turns out, because of some details having to do with quantum mechanics and Heisenberg's uncertainty principle, that even at absolute 0, the motion doesn't really stop. But let's just say, among us friends, that absolute 0 is when the motion stops. Measuring up from absolute 0, the room temperature is about 300 degrees. Ice melts at about 273 degrees. Water boils at 373 degrees. The coldest temperature that anyone has ever measured on the face of the Earth was 185 degrees. Whoa! My friends, your mother was right. You should never, ever put a closed container of liquid into the oven. And let me just use this experience to say a little bit about safety. You know, you see me doing all this stuff here, and you say, wow, that looks cool. Maybe I should do that. No. I've been working with liquid nitrogen for 50 years. I take regular training to refresh my memory about all the safety issues about liquid nitrogen. I have done things that weren't evident to you. When I took the watch off, that was to make sure that if there was any liquid nitrogen spilled on my arm, that it wouldn't get caught by the watch and give me a frostbite. I took my jacket off because the jacket could trap the liquid nitrogen, but it just rolls off my arms if it hits it. So all of these things, the way I hold the dewars when I pour them, to ensure that I am safe and to ensure that you are safe. So if you think this is really cool, then you should become a physicist and learn how to use liquid nitrogen, then you can play with this marvelous stuff all day. That's what physicists do. At least experimental physicists. No, it's true. An experimental physicist is someone who plays with really expensive toys all day. What could be better than that? But anyway, let's come back to the temperature. So the coldest temperature ever measured on the face of the Earth was 185 degrees above absolute zero. This stuff, which unless you've been in a low temperature physics laboratory, this is the coldest stuff you've ever seen. This stuff is so cold that when I pour it out, it boils immediately. This stuff is 77 degrees above absolute zero. So compare that to the coldest temperature in Antarctica, which was already 10 degrees colder than dry ice. That was 185. This is 77 degrees. 77 degrees above absolute zero. This stuff is incredibly cold. Just amazing, amazing cold. I'm not sure if everybody's gotten a good view of what this is like. This is just fantastic. But so it seems like something that's that cold, the coldest stuff you've ever seen, seems like a perfectly good thing to use as a refrigerant to cool down gas. And that's what we were doing by putting these balloons into the liquid nitrogen. But I got the feeling that a number of you were thinking that perhaps there was something wrong because the volume of the balloons that went into this bucket, which was already full when we started, that the volume of the balloons was considerably bigger than the volume of the bucket. Now, who remembers how many balloons we put in? Yes, 5?
Yes.
Does everybody agree it was 5? What were the colors? Here's the black one.
Purple,
Now,
green.
you see, these balloons went in there because they're flat as pancakes. Here's a purple one. They're easy to like frisbees. Here's another purple one. There's what about yellow? How many orange ones did I put in? What about gold? How about let's see. Here's another green one. You see, I cheated. I put a whole bunch of balloons in before we started. These balloons went completely flat. The air did not go out of these balloons because you can see, just warming up, the balloons have reinflated. So what happened? Let's go back to the laptop. If you take any container of gas and put it in contact with something cold, a refrigerant, then if it's cold enough, the gas is going to condense into a liquid or a solid, or it'll stick to the inside of the container, and you won't have a gas anymore. And that means it's not going to be useful for making an atomic clock, because this perfect ticking frequency that you get from the cesium atom is for a cesium atom floating freely in space, not one that is stuck on to other cesium atoms or stuck on to some surface. It's for gas state cesium atoms, and if they condense, this is not going to be something we can use for an atomic clock. So the problem is that we want to cool something down a lot As it turns out, a lot more than liquid nitrogen. But how are we going to cool it without touching it? How are we going to get it down to incredibly low temperatures without touching it? And because if we touch it with something cold, then that is going to make the atoms condense onto that cold surface. And the answer to how we're going to do this has been staring at us from the heavens for centuries. Because since the time of Kepler, people have known that the tails of comets always point away from the sun. So if you have a comet coming in from the outer reaches of the universe, the outer reaches of the solar system, I mean, and as it comes in close to the sun warms up the dust and the gas that make up the comet, and the sunlight pushes the dust and the gas away from the comet, so the tail streams behind the comet. And then as the comet goes around the sun and goes back out, the tail streams in front of the comet. And Kepler knew this. And he speculated that it was because of the sunlight pushing on the tail. And he was right. It turns out there's also a solar wind that affects things, but he was right about sunlight pushing on things. And we're going to use that idea to have laser light, not sunlight, but have laser light push on our atoms to make them slow down. Now, in order to understand how that works, I've got to tell you about two things. One of them is resonance. When I shine light through a gas, typically the light goes right on through. That's why we can see one another, because the air is transparent. It's why this laser beam goes to the screen without being absorbed, because the air is transparent. But for the right kind of gas and the right color light, the light will be absorbed. And if it's absorbed, it will push on the atoms. For example, if instead of air we had a gas of sodium atoms, you know what sodium is. You've seen these yellow street lamps. If you had a gas made of the kind of sodium atoms that are in those yellow street lamps, and if you shine yellow light through that gas, it will be absorbed, and it will push on the sodium atoms. But the color of the light has to be just right. If the color of the light is wrong by a part in 100 million, the atoms won't absorb the light, and they won't feel a push. Now, you would never be able to tell the difference between two colors that were different by a part in 100 million. But the atoms can tell easily because they are so exquisitely sensitive to the color of the light. So that's one thing. That sensitivity to the color of the light, the demand that the light be just the right frequency is what we call resonance. When the atoms and the light match up, then they're in resonance with each other. That's one thing. The other thing is the Doppler shift. We've already talked about that. If you move toward a source of light, it will appear to be shifted to a higher frequency, to a bluer frequency. If you move away, it's shifted to a lower frequency, to a redder frequency. The effect is not very big. If you were stopped by a policeman for going through a red light, and you were to explain that because you were moving toward the red light, that the Doppler shift made the red light look green, it wouldn't be a very good argument, because you would have to be going close to the speed of light in order for red to look green. And I think maybe the speeding violation would be worse than the red light violation. But the atoms are so exquisitely sensitive to the color that they are affected just by a tiny amount of Doppler shift. So now you've got the basic idea. So here is how it works. Now this is an idea that comes from 1975, so it's more than 40 years old. And the people who came up with this idea in 1975 were Wineland, Damel in one paper, and Hensch and Shallow in another. Now this Wineland is the Wineland who's right there. Now, what I want to point out is that these four people, every one of those four people, got a Nobel Prize for something else. What that tells me is, these were a bunch of really smart people. Because this is a really good idea, right? And they all got Nobel Prizes, different Nobel Prizes, for something else. This is just amazingly cool. Okay, so here's the idea. Imagine that I am an atom. Okay, say this atom here. and I'm moving in this direction toward that laser beam. And because I'm moving toward it, it's going to be Doppler shifted up in frequency. If that laser beam has been tuned so it's below the resonant frequency of the atom, that means when I'm moving like this, it looks like it's closer to the resonant frequency, and I'm going to absorb light, and when I absorb light, I'll go down. On the other hand, if I'm this end, and I'm moving in this direction, I'm moving away from the laser beam, so it's going to look like it shifted down and it was already too low, so I won't absorb very much light from this atom, from that laser beam. If I did, you see, I would speed up, but I don't do that very much. So going in this direction, I slow down a lot, and going in this direction, I hardly speed up at all. That's great, but it gets better. You just add another laser beam coming from the other direction. So now, this atom going this way absorbs light from this laser beam and slows down, and this atom going this way absorbs light from this laser beam and slows down. So no matter which way the atoms go, they pick out that laser beam that is opposing their motion as being the one that they prefer to absorb from, and they slow down. Now, this is such a great idea, and I want to tell you right from the start that the history of laser cooling, which started here in 1975, has spanned more than 40 years. It's produced 4 Nobel Prizes, hundreds of groups, and thousands of researchers around the world have contributed to this. It's been such a thrill to be part of that worldwide enterprise in discovery. It's just been amazing. Now, you don't have to just have 2 laser beams coming from opposite directions. They can come from top and bottom and backwards and forwards. And now, no matter which way the atom goes in 3 dimensions, it will see those laser beams that oppose its motion as being the ones that it absorbs, and it will slow down. The atom feels as if it is in a viscous fluid. Imagine that you were in a swimming pool full of molasses, full of a sugar solution, a syrup. If you tried to move in any direction, then you would feel that there was a force that was opposing your motion. The atoms feel the same way. And when Steve Chu, one of the pioneers in this area, did this first experiment in 1985, he called it optical molasses, and the name sort of stuck. You may recognize the name Steve Chu because he was Secretary of Energy during the first Obama administration, the first cabinet officer in the United States ever appointed after having won a Nobel Prize. So it was a pretty good appointment. Enough said about that. If that was all there was to the story, the atoms would come to rest, but they don't come to rest, again because of something that Einstein taught us about in 1905. In 1905, Einstein taught us that we should think about light as being a stream of particles. Now, the previous century had been spent by scientists all over the world showing that light was a wave, not a particle. And now, at the beginning of the 20th century, Einstein is saying, yes, yes, of course it's a wave, but it's also a particle. This was the beginning of what we call wave-particle duality, the fact that everything is both a wave and a particle. But it began with Einstein trying to explain a phenomenon called the photoelectric effect, and he said that light would be absorbed 1 particle at a time. We now call those particles photons. So imagine that I'm this atom here, and I just happen to be at rest. And there are laser beams coming from each side, and I'm going to absorb light, but I'm going to absorb light from one or the other of those lasers because I'm going to absorb 1 photon of light. So let's say that I happen to absorb a photon coming from that direction. Boom! I'm now moving. If I'm a sodium atom, I'm moving at about 3 centimeters per second, and I'm excited. Can't you tell? And I want to get rid of that extra energy, and the way I do it is I shoot off a photon, and in a random direction. And when I do that, there's a recoil, just like I shot off a gun. And that changes my velocity by 3 centimeters per second. Now I'm ready to absorb again. It's going to be random whether I absorb from that side or from that side. Let's say it's from that side. Then I get another kick. And now I can radiate again. But maybe I radiate in that direction. I get a kick in this direction, being very careful not to fall off the stage. And so you see, every time I absorb or emit light, I get a kick in a random direction, and that heats me up. But of course, if I start to go off in one direction, then the Doppler shift will guarantee that I'll beat back that velocity. So there's going to be a balance between the heating due to the particle nature of the light and the cooling that comes from the Doppler effect. And way back in the 1970s, Dave Wineland figured out what the temperature would be. And for sodium atoms, that temperature is as low as 240 microdegrees above absolute zero. 240 millionths of a degree above absolute zero. My friends, this stuff, which is the coldest stuff you've ever seen, is 77 degrees above absolute zero. It's 300,000 times hotter than the temperature, the lowest temperature predicted for these sodium atoms. So you can bet that people got really, really excited about the possibility of making atoms that cold. Here is a picture from our laboratory in the 1980s, in which you see laser beams coming from various directions and holding a gas of sodium atoms. This is about a centimeter apart, across, and there's about 100 million atoms in there. And the question is, what is the temperature of those atoms? Well, we can get the lights back up again now. You can't just stick a thermometer in there to find out what the temperature is. To find out what the temperature is, you have to measure how fast the atoms are going. So this is the idea that Steve Chu came up with in 1985. You start with the atoms in the laser beams held in this so-called optical molasses. They're jiggling around. If they're as cold as they can be, they would be have a temperature of 240 microkelvin, a velocity of around 30 centimeters per second. So instead of 1,000 meters per second, which is the velocity of sodium atoms in one of these street lamps, their velocity would be 30 centimeters per second. But they don't go very far because as soon as they start going in one direction, they get beat back and go in another direction. But now, turn off the laser beams. The atoms expand freely because there's nothing to keep them from expanding, and the hotter they are, the faster they expand. You turn the laser beams on after about a few milliseconds of expansion, and you measure how many atoms are left. The fewer atoms that are left, the hotter the gas is. So that way you can measure what the temperature of the gas is. And they did that. It wasn't an easy experiment at all, but they got 240 microkelvin, the coldest temperature that the theory said was possible. A big uncertainty because it's not an easy measurement. We repeated that measurement a little while later, and we got again 240 microkelvin. We did it in exactly the same way they did, and everybody was happy because here we were, in the very first experiments, we were getting the lowest possible temperature. And other people measured other atoms like cesium, and they found the same thing. They were getting the lowest possible temperature. And then we decided to do some more experiments. Always an interesting choice. And what we found out was, from these other experiments, that the molasses was not sticking the way it was supposed to. It was actually a lot stickier than what the theory predicted, and we couldn't understand that. And finally, after asking all of our theorist friends what was going on and nobody could give us an answer, we decided to make some more measurements. We decided we would make better measurements of the temperature because the temperature uncertainty was quite large, and we thought, let's make the temperature measurements better, and maybe there will be a clue as to what is going on. And because we made that measurement of the temperature, we found something quite remarkable. The temperatures were much colder than what the theory predicted was possible. This was really odd, because it's clearly a violation of Murphy's Law. So the whole idea of the experiment was to make the atoms as cold as we could. And we had apparently made them colder than we could. And not just a little bit. In the first experiments, the atoms were 6 times colder than what the theory said was possible. Well, this confused people a lot. It really made us confused. We felt like these poor devils in this cartoon who have seen something much, much colder than you would expect in the environment that they were in. And we were a little bit afraid to announce this to the world because it was so astounding. So we measured the temperature in 4 different ways before we published our results. And so other people, when they saw this, decided that if we were crazy, they would prove that we were crazy. And they went into their labs and made careful measurements and found that indeed the temperature was a lot lower than it was supposed to be. So that means that we needed a new theory. So there were lots of discussions about what the nature of that theory should be. And eventually a new theory emerged, and I wish I had time to tell you about it, but that would be for another lecture. But with this new theory, devised by Claude Cohen-Tanucci and Jean Dalibard in Paris, by Steve Chu and his colleagues at Stanford, guided by that new theory, we were then able to go back into the laboratory and figure out how to make the temperature even colder. And by 1995, we had made cesium atoms 700 billionths of a degree above absolute zero. That is 7/10 of 1 millionth of a degree above absolute zero. I want to remind you that this stuff is the coldest stuff you've ever seen. And it is 77 degrees above absolute zero. It is 100 million times colder than liquid nitrogen. Our stuff at 700 nanokelvin is 100 million times colder than liquid nitrogen. The coldest natural temperature in the universe is a little bit below 3 degrees. If you go very far into the outer reaches of outer space, far away from any galaxies or nebulae, the temperature there is about 2.7 degrees above absolute zero. It's the temperature of the radiation left over from the Big Bang. And that's the coldest natural temperature in the universe. And we're getting down to temperatures that are 4 million times colder than outer space. So when I say that this is the coolest stuff in the universe, that's what I mean. And that was just a start. Eventually, more recent advances got 1,000 times colder than that. The velocity of these atoms is less than 1 centimeter per second. This really is the coldest stuff in the universe. So, what kind of a clock can we make with these kind of atoms? Well, here is a picture from our atomic clock laboratories in Boulder, Colorado. This is Don Vikoff and Steve Jeffords, and they cool down sodium atoms, not sodium, cesium atoms down here. They launch them up into the, not into the air, but into the vacuum of that apparatus, and you see they launch them up about a meter. So instead of having a meter long apparatus horizontally, they have a meter high apparatus, and the atoms come back after about 1 second. If you toss something on the meter, it comes down after about a second. So instead of having a few thousandths of a second, they have a whole second to make these measurements. And that means that they have been able to make a clock that is better than any clock had ever been made before. For a primary standard, we call this an atomic fountain because it's sort of like this jet of water that goes up and comes straight back down. And these clocks, these cesium clocks, have a fractional uncertainty of about 1 in 10 to the 16th. That means they're accurate to better than 1 second in 300 million years. But that's just the beginning. Dave Wyman, working with single ions as the ticking clock, was the first person to break into the 10 to the minus 18 level. So he got to, is this right, about 8 times 10 to the minus 18 for a living? So this is the first time anybody ever made a clock that good. Now it's not a primary standard because it's not cesium, but what this is telling us is that probably we're going to have to redefine what we mean by a second, because there are things that can give us results much better than cesium. One of the reasons why this works better than cesium is that Dave isn't measuring a microwave frequency around 9 gigahertz. He's measuring an optical frequency around 10 to the 15 hertz. So at a frequency of 1,000 million cycles per second. So that's really high, and it turns out you can have better accuracy if you do that. But that's not the end. Just a mile away, Junyi in Boulder, also at NIST, is measuring the ticking frequency of neutral strontium atoms. And those things are good to 2.4 times 10 to the minus 18 systematic uncertainty. And results that just came out a few days ago have statistical uncertainty in the 19s, in the 3.5 times 10 to the minus 19. The accuracy at this level is equivalent to about 1 second in the age of the universe. At the National Institute of Standards and Technology, an agency of the United States government, this is what we call close enough for government work. But now you may ask yourself, where are you going to store the coldest stuff in the universe? Imagine that I want to hold my cold atoms in some kind of a bottle. Imagine that this punch bowl is that bottle, and imagine that the bottle is hot, as any bottle would be. That means that the atoms are jiggling around really fast in the walls of the bottle, and when my atom hits them, they're just going to be popped out because they're going to be hit by the fast-moving atoms in the wall of the bottle. Now, imagine you could make the bottle cold enough that, that it was as cold as the atoms. Well, then the atoms would just stick. You've already seen that with the balloons. So you can't use a hot bottle. You can't use a cold bottle. You can't use any bottle at all if the bottle has material walls. Now come over here and, oh no, I'm sorry, over here and show what's going on right here. Now get the, yeah, okay. So what I have here are little magnets. And one of the things you learned when you played with magnets when you were young is that you can push one magnet with another magnet without touching it. Do you remember the first time you held two magnets in your hands and turned them and found that they pushed each other apart without touching? Wasn't that amazing? I'm still amazed by that. And what we're going to do is we're going to use that feature that I can push on something without touching it in order to trap our atoms. Now, let's go here. Okay? Now, this is a big magnet, and this little magnet here represents our atoms. It turns out that each of our atoms is like a little tiny magnet, and this little toy magnet is representing that little tiny magnet. Now, the big magnet is pushing up on the little magnet, and right here I can feel that it's just about balancing the force of gravity. And so that means that if I were to let go of this little magnet right now, it should just float there in free space. And when I do let go of it, it doesn't float at all. It flips over and gets attracted to the big magnet. And if you ever tried to do this when you were young and playing with magnets, and you tried to make one magnet float above another, then you found it never works, not with ordinary magnets, because the floating magnet will always flip over and be attracted to the other magnets. But you learned something else very important when you were playing with toys as a child, and that is that if you spin a top, it will not fall over. And it turns out that our atoms are little tiny spinning tops. And that didn't work at all, so I'm going to have to spin it. I'm going to have to spin it by hand. Okay, so our little atoms are spinning magnets, and now this thing will not fall over because it's spinning and it will float. And that's how we trap our atoms. But, whoops. Okay, let me see if I can do a better job of making this thing float. See, it never works when you're doing it in front of an audience. Okay, now any two-bit magician can make a woman float and then pass a ring around her, carefully avoiding the wires that are holding her up. But you've never seen a magician do this. You see, this thing is really floating. This is the real thing. Now, thank you. Now let's go back to the laptop. That was the toy version, okay? So now, let's look at the real thing. So what I'm going to show you now is real atoms being trapped. So this is a cloud of cesium atoms. Whoops. Where's the sound? This is a cloud of cesium atoms that is being held in a kind of magnetic trap. And there was some really beautiful Prokofiev that went with this. But what you can see is these atoms are bouncing around just like our toy was. And as time goes on, the atoms disappear. And the reason they disappear is the vacuum isn't perfect. And so the background gas atoms hit our cold atoms and knock them out of the trap. But as time went on, and let's go back to lights, we learned how to make better vacuum and hold atoms in traps for longer periods of time. And then we learned another trick. The trick is called evaporative cooling. Now, you'll all know how evaporative cooling works. If you go swimming and come out of the water on a windy day, you feel cold. And the reason is that the water is evaporating from your skin, and it's the most energetic water molecules that evaporate, and that leaves behind water that is colder. We do exactly the same thing. We hold our atoms in a trap, a magnetic trap like this one, and we allow the most energetic of those atoms to escape, and what's left behind is colder. And then we find out another thing that Einstein taught us about in the 1920s. He said that if you got a gas of atoms of a particular kind, what we call bosons, and most of the atoms that we deal with are bosons, and got them cold enough and dense enough, something weird and wonderful would happen. A large fraction of them would stop moving. Now, at that time, Einstein didn't know about Heisenberg's uncertainty principle. It says they can't stop moving. But today, we would say they stop moving as much as Heisenberg's uncertainty principle allows. And 70 years later, more than 70 years later, out in Boulder, Colorado again, at the National Institute of Standards and Technology, and at MIT in Cambridge, a group of scientists shown here did that. They got a gas of rubidium atoms and a gas of sodium atoms so cold and so dense that a large fraction of the atoms stopped moving. This picture shows that sequence. At 400 nanokelvin, you have a broad distribution shown here. The sort of thing you would have in any gas, except this gas is 400 billionths of a degree above absolute zero. And then when we get to 200 billionths of a degree, boom, this spike shoots up. Those are the atoms that are moving as little as they are allowed to move by the laws of physics. And they cooled it down to about 50 nanokelvin, and these guys got the Nobel Prize in 2001 for making that boson constant. So now we're coming to the end of a kind of odyssey in which we have been searching for lower and lower temperatures. And this cartoon of a thermometer, a logarithmic thermometer, where each tick mark on the thermometer is a factor of 10 in temperature, is a guide to the journey that we've been on. The highest temperature on this thermometer, not the highest temperature there is, but a pretty hot temperature, the surface of the sun, at 6,000 Kelvin. You know, at 6,000 Kelvin, it doesn't really matter whether it's Kelvin or Celsius. It's really hot, right? But notice that room temperature is only a little bit colder than the surface of the sun on this logarithmic scale. And liquid nitrogen, the coldest stuff you've ever seen, is only a little colder than that. In fact, outer space, the coldest temperature, natural temperature in the universe, is only a little bit colder than that. The first laser cooling experiments with sodium in optical molasses at 240 microkelvin were colder compared to outer space than outer space is compared to the surface of the sun. And that was just the beginning. The first those condensates were again that much colder at 50 nanokelvin, and today we're down below 500 picokelvin, less than 1/2 of 1 billionth of a degree above absolute zero. And that's just a start. We're hoping that within the next few years, we'll be able to send these experiments into space on the International Space Station and maybe get down to temperatures below 1 picokelvin. Well, what's next? Well, one of the amazing things that's next is going to the other kind of particle that there is. Remember I told you that most of these atoms are bosons? Well, there are just two kinds of particles in the universe. Bosons, which are like rubidium atoms and sodium atoms and photons, and they love to be in the same state. But there's another kind of particle called fermions. Electrons, remember them? They're pretty important. They account for all the chemistry that we see. And the fact that they are not allowed to be in the same state is what we call the Pauli exclusion principle. And that's what leads to the whole periodic table and the richness of the chemistry that allows us to exist. And the person who first cooled down to the really low temperatures that we need, not rubidium, but potassium atoms, which are fermions, was Debbie Jin. Again, at NIST in Boulder, Colorado. She was the first one who got what we call a quantum degenerate gas, of fermions, which opened up a whole new avenue of research of studying really cold fermions, which are sort of analogous to electrons. Debbie died just about a year ago, at the age of 47. And we will never forget her because she changed everything about our field of research and gave us these wonderful new directions. And where are we going? Better clocks? We're already making better clocks. Dave's making some of the best clocks in the world. Junji is making some of the best clocks in the world. And they're using these clocks to test our most fundamental understanding of nature. Are the fundamental constants of nature really constant? This is one of the things that you can do with these kind of clocks better than you could ever do before. I wish I had time to tell you about quantum computers. Dave Wineland has been one of the pioneers in the whole field of quantum information, quantum computation, using single ions as bits of quantum information, not like classical bits of zeros and ones, but things that can carry quantum information and be in 0 and 1 at the same time. And the amazing things that you can do with that is a whole other lecture. Using these atoms to simulate the behavior of materials that we can't understand. For example, high temperature superconductivity. Nobody knows why that happens. We're hoping that studies of ultra-cold atoms can give us clues about what kind of mechanisms may be important for high temperature superconductivity. And maybe the most important thing are that we haven't thought of yet. And it may be that some of the young people in this room will be the ones who will come up with the most important new ideas. And it may be that here in Brazil you will study things like in São Carlos, in Vanderlei Granada's laboratory, they're studying turbulence in superfluid systems. And you may join a group like Vanderlei's group, in which people from all over have come together to study the mysteries of the universe. Or a group like mine at NIST, where people from all over the country and all over the world have come together to explore the mysteries of the universe, to try to tease out new knowledge from these new directions of research that we have. And so we've come to the end, but you know, it's never really the end because there's always something new to learn. Thanks very much.